So we are starting our class. Class is going to be in English. So if I'm not wrong, we're going to study here advanced statistical mechanics. This is my first time that I'm teaching this class, unlike the regular statistical mechanics, whoever took this class with me. My name is Stas. My location is down the hall, office number 314. The email over here. All this information also is going to be available on the Lambda site. Some technicalities about the class. So it's the same construction as for the regular statistical mechanics class that some of you took last year. So the final exam is 67%. There is going to be a midterm quiz, which is 22%, and homework mandatory each week, that is 11%. Your TA is going to introduce, well, the TA, she's going to teach you just after my class, so from 6 to 8, and she's going to be responsible for the homework part. What else? Well, that's it. This is the technical parts. Any questions about that? No questions. Great. So
is there a date to the quiz?
It's going to be in the middle of the semester, approximately. I think around Hanukkah. Around Hanukkah. If maybe a little bit before or maybe a little bit after, but this is something in the middle. One thing that I can tell you about the quiz, that it's magnetic. Basically, it cannot lower your grade. So if you're getting, if your mark in the quiz is going to be lower than your final exam mark, we won't consider it at all. Then your final exam is going to jump to 89%. Okay. All right. If there are no further questions, I will start. So please feel free to interrupt me at any time, at any point. Now, the starting point of this class is that I assume that you do know statistical mechanics. Okay? If you do not know statistical mechanics, well, it's going to be tough in this class. What do I need you to know from statistical mechanics, at least at this point, is the Boltzmann-Gibbs picture, okay? Which is used, and we use this in the regular statistical mechanics class, to transfer from the micro description to the macro description. What do I mean by that? So if we have all the possible momenta and positions of different particles, or we have the different quantum states of the matter, or we somehow quantized, although we have a classical system, but still we quantized some states, and we know the different states of the system, and we know the different energies of the state. At least in the canonical perspective, what we know, if we know the states, if we know the positions, if we know the momenta, so if we have a lot of information about microscopical information about the system, we can construct the partition function. Okay. The different parts in the partition functions, those e to the power minus beta ei, where beta is 1 over k Boltzmann T, T is the temperature. Those are the Boltzmann factors that determine the probabilities of finding the whole system in some specific state. So it's not finding one specific particle. If we have just a system of one, which is constructed of one particle, of course it's for this one single particle. But generally, those probabilities are for finding the system at different states. Okay? So this is the microscopical perspective. The moment that we have this, okay, all of this information, we can calculate the free energy. Right? So the free energy, which is going to be defined as 1 minus 1 over beta, a logarithm of the partition function. Now, from the free energy, you can calculate any macroscopical quantity that you want. You want to calculate pressure, you want to calculate magnetization, feel free to do it. So this is already a macroscopical description. So the Boltzmann-Gibbs perspective, if you know everything in the microscopical world, you will know everything in the macroscopical world. Okay. So this is what we have done in a class on regular statistical mechanics, and basically that's it. There is nothing more in statistical mechanics almost at all. You know this, you can calculate that, you're free to go. Okay. Now the question is what we are going to focus in this class, because you somehow know everything, right? The thing is, what else there are that we haven't covered in previous classes? Some specific examples, maybe quantum information or quantum potentials, or the axioms why all statistical mechanics is applicable, because there is a funny thing over there. We cannot solve anything for mesoscopic system or a system that constructed of small number of particles, and we can solve a lot of things for systems that are constructed for many particles. So there's those axioms over there. But this is not actually what I'm going to focus in this class. I'm going to focus on something different, which we haven't treated almost at all in the regular statistical mechanics class. And this is interactions, interactions, and interactions. So if you remember, almost all the examples that we solved, everything that we ever solved was for systems that somehow described a non-interacting picture. So this is very easy to say, obtain all this information and then you're done. The problem with this partition function was that everything was, the moment that everything was correlated, I had no idea how to treat or how to solve this partition function. It's not just a technicality. It's a real problem, because the only thing that we know is how to compute this. The only way is to somehow represent our system in a form of non-interacting particles, or non-interacting quasi-particles, or non-interacting something. Only then there was a factorization trick, and then I solved everything. The problem is that most of the materials around us are actually interacting. So you take a regular solid, there are interactions. You take anything, there are always interactions. So what we are going to do in this class is to find a way how to treat those interactions. And those interactions, they actually lead to spectacular behavior of materials, physical systems, biological systems, whatever you name. So I just want to describe to you one simple example. Okay, and this example is what is called la ola. Okay, in Spanish. Where is Joseph? He's not here.
He's abroad.
He's abroad. Okay. So the Spanish-speaking guy is not here. Okay. So this is what is called the Mexican wave. Do this. So I'm not really going to stadiums, and I don't think that the stadiums in Israel are really packed in order to create something like that. Okay. But this is a wave that's traveling through the crowd. Whatever is the people are doing is just standing up and sitting down. Okay. So let's see another picture of the same phenomena. Okay, so this is a little bit more clearly showing. So the only thing that happens over here, that people are looking to the left-hand side of them or on their neighbors, and whenever the neighbor stands up, they also stand up, and then they sit. Okay. And then we have a collective behavior. Okay. So it's not something very particular to one single person. You can say, well, yeah, there are some small interactions, but those interactions are not about everybody in our stadium. Those interactions are for I don't know. Those interactions are for just considering very local range. Okay? What I mean by that is, just let me cancel this. What I mean by that is, in the example of this Mexican wave, people are looking to the left-hand side. What I mean by interaction is that I look on my neighbor stands up. After a while or after a second, I also stand up, and then I sit down. So there is an interaction, but those interactions are very, very local. They're very local interactions. Still, they create a collective behavior of macro scale. So those are people, right? And they are really not organized. It's not that there is, some coordinator jumping row 5, now you stand up. Now row 6, now row 7, etc., etc., etc. So there is nothing coordinated on a large scale, meaning there is no brain that watches and makes all these people come to stand up. Those interactions are purely local. But still, there is a collective behavior that happens, and here it's not a material, right? It's just a bunch of people that are sitting and deciding that, well, it's a nice thing to stand up when my neighbor is standing up. So we see that this, just due to very short range interaction, creates something that you can never obtain from a bunch of particles, people that don't care about each other. Okay. So if what we normally solve in regular statistical mechanics, eventually it's a gas system. People that won't care about each other won't create a collective behavior. Only due to presence of some sort of interactions. Those interactions can be extremely simple. Like in this case, it seems to you that it's like unbelievable, but you can run a simulation, and in your simulation you have just 2 state particles. The particle is either up, the person stands up, or it's down, the person sits. Okay? You excite it a little bit, and you will have those waves traveling in a circle. Okay? And the only thing that you need is low enough temperature and those interactions. So if I don't care about my neighbor, those long-lived standing waves won't appear. But if I do care about my neighbor and the temperature is low enough, I will see this. Now, what do you think is temperature? I'm using a physical quantity, but I'm talking about people. Okay? It's not that the temperature of everybody over there is 36.7 Celsius. So what I mean by temperature, what do you think?
Maybe we can analog it to, I don't know, something like fog, if I can see my nearest neighbor.
Okay.
Maybe
but you always, let's assume that you always can see your neighbor.
No.
You always can see your neighbor. So, yes.
Maybe it's better the randomicity of the system.
Great. So the only thing that, think about what is temperature. Temperature eventually that I'm jiggling for a single particle, that I'm jiggling randomly around myself. Okay. So if you think about the crowd, when I'm saying to you, well, yes, I have a person that can sit and can stand up, and it's doing it accordingly to whatever the neighbor on the left-hand side is doing. But the temperature is also saying, well, you can also stand up or sit down on your own without caring about who is over there, sitting or standing or whatever. So when I'm saying the temperature is low enough for this system, is that I prefer to sit down most of the time. If all this crowd spontaneously, every person in this crowd will stand up and sit down and stand up on its own, you won't see any wave. So the wave and this collective behavior occurs because most of the system, most of the time, are sitting down. They're preferred to stay in a specific state for a long time. It's only when their neighbor stands up, they are excited, and they stand up too. So this, for my system, which is people, this is my temperature. The temperature have very different meaning, and it very much depends on the system. For regular atoms, it's the regular temperature that we know is just jiggling of the bow of them. For people, it's also some sort of jiggle, but when I say jiggle, it's a randomicity of their position. Great. So what we are going to do and how we are going to treat those interactions. So what we are going to do in this class is to treat interactions, and the most modern way to account for interactions and to use them, and not just assume, well, they are dismissible. If I will neglect all the interactions, nothing will happen. Collective behavior appears when there are interactions. And the most recent way to deal with it is statistical field theory. So, in this class, we will try to develop principles of statistical field theory and see what happens when we use the methods of statistical field theory. So we were going to use fields instead of particles a lot. We're going to use symmetries. We're going to use perturbation theory. And we're going to develop their normalization group. So those are the general themes that we will try and develop in this class till the end of the semester. Now, most of the examples, if not all of them, are going to be classical. So it's not quantum field theory, it's statistical field theory. The approach is statistical. In a lot of cases, the systems are going to be classical, but the methods are very, very, very similar. So if you know quantum field theory, you're in the right spot. If you're not, well, don't bother, because I will teach you whatever is needed to know, whatever you need to know about this field. All right, so let us start, and I will try to use this example. Any questions so far? Yes.
It's a main book that we can reference.
All right, so there is no main book. There are several books, and I will put this list on the Lambda page. Right. It depends. So specific parts are going to be from one, the other parts from the other. So nothing that I really follow. Yes.
There's maybe notes in the Lambda.
Notes. This is the first time that I teach anything. Yes. So this class was taught by Ido Kanter for the last 30 years, I think. So Ido taught me. You know Nadav, so I think Ido taught Nadav. So this was a class of Ido for a very long time. And I once was like you, sitting over here and studying this material. And this is the first time that Ido retired, and now I'm teaching this. So no, not so far. Okay. But everything is recorded, as you know, and I will try to produce notes. Okay? And if I will produce something that doesn't look like, tell them that there are no notes, I will publish it, right?
The presentation will be up.
This presentation, those 3 slides?
Okay.
Sure. If you like, I can put it on. But it's just something that I'm telling you to burst your curiosity. All right. Any other questions? So the idea for me is to say, well, we look on the spectators in a stadium, and I'm saying, well, the spectators in the stadium somehow behave eventually for physicists like particles or like atoms. And all those atoms, right? When I try to model atoms, or when I try to model something that's constructed of atoms, I will always say, well, those just particles connected by springs. So, in this class today, I'm going to try and develop and show to you how I'm starting from a microscopical description, okay? Microscopical model springs and particles, and I'm going to a field representation and force gradient. So this is what I'm going to try to do today for a simple example of particles connected by springs. I suspect that maybe parts of what I'm going to develop here you've seen in other classes. Nevertheless, I'm going to repeat this, well, because it's actually fun. So this is, you can call it as a field theory for elastic representation. And I'm first of all going to describe to you lattice vibrations on a ring. So consider the following system. I have a single line. On this line, I have particles. The equilibrium separation between the particles is A. Okay. Now, moreover, it's a ring, so I don't have boundary conditions for simplicity. And each particle, so this, let's take this particle number I, the position of this particle or distortion of this particle from its equilibrium position, it's ui, right? So un, or un, particle number n, un distortions, and I also have Pn momenta. Okay. So when I write it like this, I'm saying that my Hamiltonian, it's a classical Hamiltonian, so I know how to write it. It's very simple. So it is n goes from 0 to n minus 1. So I have n particles in total of Pn squared divided by 2m. And I have the following potential energy, which is quite complicated. So it's 1/2 a sum. R goes from 1 to R, K of R, to large case. A sum m goes from 0 to n minus 1, un plus r minus un squared.
What is R?
What is r over here is basically the length of the interaction. So what I'm saying is, let's look on particle number n. When r equals 1, I'm only interacting with my nearest neighbor, n plus 1. This is un. This is un plus 1. When r equals 2, I'm considering the next nearest neighbor's interactions. So here it's n plus 2. Here it's n plus 2. When r equals 3, I'm considering not the interactions with the nearest neighbors, not the next nearest neighbors, but the next nearest neighbors. N plus 3, un plus 3. So I'm saying everything is connected by springs. Those KRs are spring constants that determine my interaction with whatever particle that I'm interacting with. So it's not just I have springs that connect two particles and that's it. I'm also saying this guy affects that guy directly, and this guy affects that guy directly, not by affecting its nearest neighbor, but everybody are interacting. How they interact? Well, I'm assuming particles that are connected by springs, so they everything interact in Hookean fashion, but I have a finite region of interaction. So this R is finite, large R. So eventually, it's not that everybody are interacting with everybody. I still have a finite range of interactions. Okay. Yes?
We can imagine that n and n plus 2 is also connected to springs?
Yeah. So you go to everybody, and everybody are connected. So n plus 2 connected by n to n plus 3, and connected to n plus 4. This is why you're running here on all different n's and all different r's. Okay. Great. So this is my Hamiltonian. There's a lot of terms in this Hamiltonian. Okay, a lot of mixed terms, not just nearest neighbors, right? And I want to make something out of this Hamiltonian. So how do I proceed? So what I'm doing right now, I'm trying somehow to diagonalize my Hamiltonian, right? Why? Because this is how I know to solve anything, right? In quantum mechanics, in classical mechanics, my Hamiltonian have to be diagonalized. I know to solve basically two problems: non-interacting particles at all, and some harmonic non-interacting particles. Okay, so this is what I'm trying to do. Okay, so how are we going to diagonalize this guy? Well, instead of trying to diagonalize it, we say, let's represent everything by Fourier transform. So we have Fourier transform, and it's actually discrete. Fourier transform, why discrete? Because I have a lattice. The moment I have a lattice, there are specific k's and specific x's that are have to be present. So I'm saying the following. I will represent any distortion of any particle n as 1 over square root of n, a sum. N goes from minus n to m, so it's going to be symmetrical around 0. I have positive case and negative case of e to the power I k m and a u tilde of m. What is km? Km is 2 pi m divided by, pi m divided by n a. Minus pi divided by a plus pi 2 pi divided by n a n. So those are my kn. The positive case, negative case, and everything have to be symmetrical. So if this is un and this is the Fourier counterpart, I can also say that um tilde, okay, it is 1 over square root of n. This is square root is just for the normalization of everything. A summation, n goes from 0 to n minus 1. E to the minus 1 k m n a u n. Okay, so this is the Fourier representation of un. This is the regular representation of un tilde, right? And now I'm going to represent everything by using this Fourier transforms. Now, before I proceed, I will need two identities. So what is the identity that I will need? I know that when I sum up, n goes from 0 to n minus 1 of e to the power I km minus km prime and a, this is just a canonical delta function.
אז אומרים פה שההרצאה הפסיקה להקליט.
I don't know. So this is just n delta m prime. Okay. Where is this coming from? Oh, those are properties of the Fourier transform. Okay. So for my case, it is n goes from n minus 1 e to the power of km plus km prime and a. So this is just n delta m prime minus m. Where those relations are coming from, well, those are just orthogonal properties of the representation by using Fourier transform. What else will I need? I will need the following thing. Look on this guy. So I write down um tilde equals to 1 over square root of n, as summation n goes from 0 to n minus 1, e to the minus I km and a u of n. And I will take a complex conjugate of this guy. So taking a complex conjugate is taking a complex conjugate from the left hand side is also taking a complex conjugate on the right hand side. And what it gives me, the complex conjugate on the right hand side, so once square root of n stays the same, the sum n from 0 to n minus 1 stays the same. I have a complex conjugate of this exponential. Okay? What this complex conjugate does, it only turns minus I to I. So it is e to the power I k m n a u n complex conjugate. Great. Now, what is a complex conjugate of un? What is un? What is un? Those are distortions. They are real. So the complex conjugate of a real number, it's the same number. So complex conjugate of un is just un. So I have over here 1 over square root of n, a summation, n goes from 0 to n minus 1, and here I have un. Okay? Now, this is not exactly the way to write a representation of un. I'll write it down as e to the power minus I minus km and a. What is km? Km is minus pi I 2 pi m divided by na. So minus km is just km. Right? So it's basically saying, oh, minus km is just k minus m. Minus km equals to k of minus m. So what we have, sorry?
מינוס km שווה ל-k של מינוס n.
Substitute it over here, and we'll find it. They are symmetric. So you go for to m or to minus m, they are absolutely symmetric around 0. So what I have is it equals to 1 square root of n. N goes from 0 to n minus 1, e to the power minus I, k minus m, n, a, un, and this is u tilde minus n. So the third relation that I'm going to use is that u m complex conjugate, it is u tilde minus m. Okay. So my idea is to take this large Hamiltonian, use the Fourier transform to represent every un over there in terms of um tilde and um tilde, and use this orthogonal relations and complex conjugate relation from m to minus m in order to obtain the form of the Hamiltonian in Fourier space, discrete Fourier space.
I must have missed something, but why can you assume orthogonality?
I assuming orthogonality.
But
Why? Sorry? Why assume? This is a property of the Fourier, discrete Fourier transformation.
Just from the Fourier.
Yeah, it's those e to the power i's, they are also orthonormal when I use the 1 square root of it. That's it. Okay. So it's nothing to do with un, it's everything to do with whatever representation I'm using. Great. So now whatever we had over here, it's a long representation, but everything was about un plus r minus un. We had a lot of functions to the second order over there. So I'm going to describe this difference not in real space, but in Fourier space. Okay. So what we are doing, let's look on this in the following fashion. So first of all, let's look without the square. It's un plus r minus un. So un plus r, it is 1 over square root of n, a sum. What is this? N goes from, m goes, we sum over m, from minus m large to m large, e to the power I, k, m, n, a, u, m, tilde. But we don't have n, we have n plus r. So it is n plus r, a, minus, sorry, it's u, m, tilde, minus 1 square root over n, a summation over m, yes.
M plus r in the
N plus r.
Also in the um tilde.
No, because it's m. M is the index in the Fourier space. N plus r is the index in the real space. Right? I'm computing this guy. So this is un plus r. Look on the definition. Okay, so m runs from minus m to m, but n stays constant, and it's related to the index over here. So again, a summation over m, e, I, k, m, n, a, u, tilde, m. So in total, I have the following. It is 1 square root over n, sum over m. I have here e to the power I, k, r, a, minus 1, e to the power I, this is k, m, I, k, m, n, a, u tilde over m. So this is the difference un plus r minus un. Now we have a bunch of terms that look like un plus r minus un to the second power, etc., etc., etc. So let's first of all compute what happens for r equals 1. So those are potential energies that correspond only to the nearest neighbor's particles. Okay? I'm taking 2 particles, nearest neighbor particles that are somehow connected to a spring, and I calculate this difference in a Fourier space. So this is the formula that we are using. It is a sum over n, un plus 1 minus un to the second power. Right? So we run over all the particles, and for all different particles, we compute the contribution to the potential energy only from the nearest neighbors interaction. Great. So this is what? This is a sum over n and inside I have this guy squared. So let's write it down a little bit differently. So it is 1 square root of n sum over m e to the power I k m r a minus 1 e to the power I k m n a u tilde of m, all of this squared. So it is a sum over n. Let's take 1 over square root of n out. So we have 1 over n. And here it's a multiplication of two sums. So the first sum is a sum over m e to the power I k m r a minus 1 e I k m n a u tilde of m, and I have another summation m prime e to the power I k, just instead of r we have 1, okay, and here we have also 1 because we are using r equals 1, e to the power I k m prime multiplied by a minus 1 e to the power I k m prime n a u tilde n prime. So we see that we have two indices, m and m prime. I will write it down as a summation over n, 1 over n, a sum over m, a sum over m prime, and inside I have e to the power I k m a minus 1, e to the power I k m prime a minus 1, and here I have e to the power I k m plus k m prime and a um tilde tilde prime. Great. What I do over here, I have to use some of the relations that are written upside over there. I have a sum over n, right? And I also have this part inside my long summation. Now, look at this guy. So the only thing that I need to do, it's very, very long, but eventually all of those sums, it's always works like that. You find something, somehow, that looks like a delta function. And here I found it. Right? I have a summation over n, I have this guy over here, right? That's it. So I just switch the summation. So instead of first summing over n and then summing over m and then summing over m prime, I sum over n, I sum over m prime, and then I sum over n. And the summation over n with this guy, it introduces a delta function. And this delta function says, well, forget about the m prime. The only thing that you need to do is cancel the summation over m prime and use this minus m4. That's it. So after I substitute this function, what do I get? First of all, I get rid of this summation. and this term, I get over this summation, and everywhere but I see n prime, I stick minus m. So eventually, we're getting, green is not good, a sum over m e I k m a minus 1 e I k minus m a minus 1 u m tilde u tilde minus m. Where did 1 over n go? Why don't I have a 1 over n in this part? Because of the delta function. Okay, so there was n in the delta function, and the moment that I substitute it, it cancels out with the n over here. Okay. Now, this is already really nice. Why this is nice? Because, well, I know what is u tilde minus m. U tilde minus m is just um complex conjugate. So I have a sum over m e to the power I k m a minus 1 e to the power I k minus m a minus 1.
You can replace this also.
Sorry?
K minus m.
K minus, right? K minus m. How do I replace it?
Minus
Minus? What is k minus? Right. You're absolutely right. So we also use this k minus m equals to minus km. Right? Because we used a symmetric case with respect to 0. Great. And here, I'm using this relation. Great. So we have u m tilde complex conjugate. We're almost there. Why are we almost there? So we have a summation over m. Okay. We have all of this complex conjugates, but it's actually not that difficult anymore. So we have summing over m. Instead of this guy, what is a function multiplied by its complex conjugate? This just absolute value squared, right? You take a number, you multiply it by its complex conjugate, it's just this number, absolute value squared. What we have over here, so let's multiply everything. So this guy multiplied by that guy is 1. This guy multiplied by minus 1 is minus e to the power I k m a. This guy multiplied by this guy is minus e to the power minus I k m a. Minus 1 multiplied by minus 1 is plus 1. This looks not bad at all. What we obtained is, look on this. So this is 1 plus 1, and this is minus. So this is minus 2 cosine of k m a. So in total, we obtained that this is a summation over m of 2 minus 2 cosine km a squared average. Remember what it was? This was contribution from nearest neighbors interactions. For r equals 1. We can call it dr equals 1. Now I have to repeat everything for r equals 2, r equals 3, r equals 4, r equals 5, etc., etc., etc. And you know what happens when I do that? So if I do dr equals 2, I write everything down like I used it for r equals 1. I represent everything with this Fourier transform. I change the summations, etc., etc. And finally, where I'm getting to is that it's a sum over m, 2 minus 2 cosine 2 km a um squared. Okay? The only difference is this 2. And if I do it for VR equals 3, I'm getting that it's a sum over 2 minus 2 cosine 3 km a squared. This is tilde, tilde, tilde. This is tilde. And I'm doing this for any small r. So now we're going back. So what is our V, the potential energy? Remember, it was a sum over r, right? R goes from 1 to r. Right? Here I had k r. Okay. And instead of all those contributions for r equals 1, r equals 2, r equals 4, I'm writing down those expressions. V r. So if we'll substitute everything, we'll have a summation r goes from 1 to r, summation over m, 2, here it's k large k r, 2 minus 2 cosine r km a tilde squared. Let's switch the rows of the summations, the order of the summation. So I have a summation over m, a summation over r goes from 1 to r of 2 kr 1 minus cosine r km a. We'll put a parenthesis over here. tilde squared. Sorry?
Okay.
So there was a 1/2 over here. 1/2 just kills this 2 over here. What is this? This is a normal mode representation of a very general potential where everybody can ever interact with a large number of particles, not just with their neighbors, right? Because we can write it down as summation of m. No, I'm sorry, I will have this 1/2 and I will have 2 over here. I will explain it to you why. So 1/2 omega of m, right? tilde squared. And this I will also say this is a square. Where what is my omega? omega squared m equals to a summation r goes from 1 to r 2k r 1 minus cosine of r km a. Yes.
They are saying the camera isn't working in the Google
Sorry?
Meet. They are saying the camera isn't working in the Google Meet.
Again, but please raise your voice.
Camera in the Google Meet isn't working.
Camera is not working?
Yeah.
There should be a technical helper over here. If he's not or she is not, there's nothing that I can do. Okay?
Don't you miss like m omega squared?
Okay, so let's correct it in a second. Fine. Now, what I managed to achieve eventually in my elastic representation I'm looking on my potential, okay, and in my potential perspective, I'm saying, or let's look on the total energy, my Hamiltonian. So my Hamiltonian was the kinetic energy plus potential energy. The potential energy is just the sum of oscillators with very specific omegas, right? The kinetic energy, okay, it's also exactly the same, right? Because I just have what is a kinetic energy? Kinetic energy is just a summation of 1/2 p m squared, was pn squared to omega here. So this is what I have. If I would transform it into Fourier space using exactly the same methods, as I did before, I will get Fourier transform, exactly the same Fourier transform. I will get that this is a summation over m, Pn, so let's use this as, we have small mass, so we have a large mass m, of p m tilde squared divided by 2m. This is mass of the particle. So we have kinetic energy, which is quadratic. We have potential energy, which is also quadratic. The potential is very, very, very general, but still I can decompose it into normal modes representation. All those modes, because it's just a sum, so it's a sum of oscillators, there is a sum, independent sum. There is no multiplication of m and m prime or m and m plus 1, etc., etc., etc. They are all absolutely independent. So what I'm saying is, hey, look, I can look on those um tilde, and I know that each and one of them is just a simple harmonic oscillator, right? So it is 1/2 um, 1/2 the energy of mode m is 1/2 um tilde dot squared, okay, divided m plus 1/2 omega m squared um tilde squared. Quadratic energy for the kinetic part, quadratic energy for the potential part. So I have just a bunch of oscillators, and this omega over here, omega m squared, it's a sum of r goes from 1 to r of 2k r 1 minus cosine r km. So the point of this exercise, was we take a system. Well, this was a one-dimensional system. And when you know everything about the potential, what I mean by knowing everything about the potential, I know that all interactions were quadratic, but there were mixed interactions between many, many different particles. So when you know those KRs, you can always diagonalize it, okay? And you'll obtain a behavior of simple harmonic oscillators which are uncorrelated, unrelated, and do not affect on each other, okay? So this is what we've done. How this omega m looks like? Well, it's a complex function. It's a big sum of different stuff inside over here, right? But, well, maybe it's not that complicated. Maybe it's not that complicated. Why? First of all, it's very important that I have harmonic oscillators, okay? And I'm saying, well, although I can, this omega m, it's related to k of m in a very peculiar manner. We have cosines and those krs over here. But I'm saying, well, it's actually not that important. Why it's not important? So if we have harmonic oscillators, we know the following thing from statistical mechanics. Each harmonic oscillator, if I'm describing it as a quantum harmonic oscillator, I know that the occupation number, n, right? So I know if it's a quantum harmonic oscillator, E of n is what? H omega n plus 1/2. Okay. So if I'm saying, if this is the energy of harmonic, yes?
Don't you mean like capital M omega squared?
Capital, oh, this guy?
Yes, like a masculine? Oh. No, only on one side.
Okay, yeah.
Yes.
Yes. So if you look on particle number n, mode number m, if it's quantum oscillator, like we did in the statistical physics class on debye, this is the different energetic levels. Okay? Now, if you compute the occupation, okay, you will get that the probability or the average energy, which is dependent on m, so you forget about this 1/2, right? So it is just HW divided by 1/2 plus H bar W average n. Call it an m. Here it's n. So I have 1 over squared H bar omega plus H bar omega, and here I'm going to have what? E to the power beta h bar omega minus 1. So if you don't remember how to calculate this average number, go to the statistical mechanics class. I show it every year. But this is the description. Yes?
This is the average particle number?
This is the average occupation. Yes, yes. Not particle number. So average level number, you can say. Right?
But this is only for one.
This is only for a very specific oscillator.
Yeah.
Number m. Okay? Now, the only thing that matters, you don't care about this guy. You care about that guy. Why? Because this depends on the temperature. This can be just a constant you don't really care about. Okay? Now, if I plot h bar omega divided by e to the power, or 1 over e to the power beta h bar omega minus 1 as a function of temperature, I will get this transition. Okay. Due to the exponential over here. Eventually it will decay to 0 and it approaches some specific h bar omega, some specific number over here. Okay. Now what it means, I'm sorry, as omega. Means when omega is small, I'm sitting over here. So for small omegas or small temperatures, the only thing that matters are, for small enough temperatures, the only thing that matters are small omegas. Because, well, this guy for large omegas is going to contribute almost nothing. So the main contribution is coming where from? It's coming from small omegas. Okay, so I need, in this expression, for low enough temperatures, only consider the situation where omega is small. Okay? And where from this small omega is coming? The small omega is coming from small km. So small k's contribute to small omegas. Why do I need only small omegas? Because large omegas, okay, are unoccupied. So I take this guy and I ask myself, what happens to omega m squared, which is 1 over m, sum r goes from 1 to r, to large K r, 1 minus cosinus of r k m a. So omega goes to 0. What are the main contributions? The main contributions are also coming from k goes to 0. So I don't need all this cosine behavior, etc., etc., etc. Why? Because I'm looking in the small omega limit. Small omega limit, because I'm looking on low enough temperatures. Small omega limit, small k limit. What happens in this small k limit? Oh, I need to expand 1 minus cosine r k m a. Taylor expansion. So when km goes to 0, cosine goes to 1. So there is 1 minus 1 minus 1 half r squared, k squared, a squared. In total, I obtain that this is 1 half r squared, k squared, a squared.
Can you say again?
Sorry?
Can you say again why when omega approach to 0, also k approach to 0?
Well, I'm expanding. I'm using it the other way around. When k approach to 0, okay, let's look at it from this perspective. When k approach to 0, I can Taylor expand this guy, right? So I have 1/2 r squared k squared a squared, right? So omega m squared is going to be 1 over m. A summation r goes from 1, and k goes to 0 limit. R goes to 1 to large r, large k, small r, and there I substitute this. Oh, I had 2 multiplied by 1/2 km squared, right? R squared, a squared. So I'm obtaining this is 1 over m. A summation r goes from 1 to r, kr multiplied by r squared, multiplied by a squared, multiplied by km squared. Okay, so you see when k goes to 0, also omega goes to 0. I'm saying since I'm looking in the omega goes to 0 limit, right, I have to take the k goes to 0 limit when, but you're right, maybe there is some other limit when k does not go to 0, but omega goes to 0 and I'm neglecting this limit at all. Okay? So I'm saying when k goes to 0, omega has to go to 0. Maybe there are some other case where that are not 0, that for them omega is 0. I forgot about that. Okay? So what all of this bunch of a lot of summations, etc., means, and this is eventually what you need to learn from past hour. Several things. So first of all, when I'm looking on the strings, etc., I can decompose it to normal modes. Okay? Moreover, I know that the frequency of each mode is what? In the k goes to 0 limit, it is c k m. So I got sound or phonons or whatever we want to call them, right? So this is the dispersion law. Okay. The result of everything that I have done over here is that when we take springs, we somehow interconnect them. But eventually we have only springs. They can have various coefficients, etc. When I lower the temperature, when I lower the temperature I have to be in this limit. So only the states with small omegas are occupied, and in this limit, when small omegas are occupied, those omegas have this sound wave-like or phonon-like behavior. And that's all that matters. What I'm saying is, when I'm looking on omega, the function of k, and this is the first Brillouin zone, have to be from minus pi by a to pi by a. In the small k limit, even in this very strange potential, with a lot of interactions, eventually I will have this phonon behavior. I will have sound waves. What it means that those deformations will deform somehow all together. Right? What I will have over here, I don't know. I don't really care. Because the only thing that I can say, well, in the very low temperature, I will eventually have only small omegas occupied, small k, large length wave, and this whole thing will move somehow together. And I'm working in this limit. So this is C, K. But the thing is, okay, the C, the sound wave, I know exactly what it is. 1 over m, a squared, a sum R goes from 1 to R, and here I have KR, R squared.
Should it be square root?
Square root. Square root, you're right. Square root. Right. Okay. So this is the point. If you lost me somewhere in those calculations, don't worry, it's fine. The final picture for the springs and particles on one-dimensional line, the only thing that I want you to remember and understand is that in the low temperature limit, even for very complex potentials, and we chose a very complex potential because we could choose any KRs over here. Those coefficients can be whatever we like, as long as they are positive. So the potential can be very, very, very strange. Eventually, in the small temperature limit, we have sound waves. The system are excited from doing nothing, doing something in a sound wave-like motion. Cooperative motion, okay? Not local, but global, because lambda, the wavelengths of those sound waves, is proportional to 1 over k. And we're sitting in this very small k regime, so the wavelengths are very, very, very large. How we obtain it? By using Fourier transform, etc., etc. Right. So if I'm starting from a microscopical model, in a lot of cases, like in this case, I can work extremely hard and eventually obtain something that's, well, it's quite simple, right? And I can explain to you all the different parts, okay, in the effective motion, at least in this limit of small temperatures. Okay, so we have cooperative motion because everything is just doing something like that, right, at the small temperature limit. My question is, can I do something similar without knowing what is the potential? Okay, so here I had to work very, very hard, and I could do it because the potential was harmonic. Okay? And eventually I know everything about the system because I know all those k's of R over here. Give me the k's of R, I will plug it inside, and I will give you the speed limit. But what if I don't know the k's of R? Right? And the approach that we are going to take, well, a little bit today maybe, it's somewhat different. So our approach is, this is the approach of the field theoretical perspective. The approach is somewhat different. For one, forget about the microscopical details. Okay. Two, construct an effective potential based on the symmetries of the system. So what do I mean by that? Don't worry, I won't go deep into mathematical description right now, but I will just explain to you what I'm going to perform next week. Think about this one spring with masses that we have. And what we know that in the low temperature limit is just they oscillate. Okay? So if I'll plot my one-dimensional line, I'm knowing that somehow everything is oscillating all together. So I will have distortion, so that I'll have specific regions where those particles are dense, and specific regions where they are less dense, and then they are dense again. And they are, again, sparse. So this is the behavior. Dense regions, sparse regions. Dense regions, sparse regions. Because everything is doing something like that. They are moving together in a sound wave-like motion. And I know everything about the microscope. Field theory, for me, is like, I don't know whatever happens over there. I don't know where all the different particles are. But I know the following thing. I will somehow, instead of looking on specific positions of the particles, I will try at each point x define a distortion field. I will define, instead of saying u of x, what for me is going to be u of x? I will look on a specific window of the size L. And for this specific window, I will produce one single number, which is this u of x. Okay. So think about it as like an averaging. I'm looking on this guy. So in this case, I have 3 particles, but assume that I have 24,000 particles in my L. Okay, and I, instead of saying, well, this particle is over here, this particle is over there, this particle is in some other position, I will average it and produce to you one single number. This procedure is called coarse graining. Forgetting about the microscopical positions, okay? Because if I know them, well, I can solve, I can work very hard, and for simple cases I can solve them, but it's a dead end eventually. This approach is different. Is saying, look on all the line. Average somehow whatever happens on the microscopical scales and produce, instead of saying the positions of 3 particles, produce for me a one single number. What is this one single number? It's a distortion. Okay, so let's assume that this is u of x, this is x. So u of x describes to me how dense the particles in specific positions are. Okay, so if I'm having sound waves, I'm assuming that u of x will look something like this, right? But this u of x is not that, oh, here one single particle that is distorted up here. No, it's something that I have done to a bunch of particles and decided that this is what u of x represents. The moment that I have coarse grain perspective, still perspective, the next step is to construct a potential. Beforehand, I have explicitly given you the potential with all the coefficients, with all the interactions. So everything was completely explicit. And it was a nightmare of all those sums, but I could still do something, right? Here is, well, give me u of x, and I will construct an effective Hamiltonian for you, which is based on the behavior of u of x at different positions. Okay? How exactly I'm constructing it? I'm using symmetries. I'm using dimensionality, and I'm using locality, okay? And I'm using the assumption that everything is analytical. Okay? I will show explicitly how it's done, but eventually I will, instead of giving you the potential, I will construct something that is based on this coarse grain u of x. Yes?
Does the graining of thinning must be linear or can it be logarithmic?
So, great question. It really depends on what scales you want to look on. Okay? So if you want this L is actually limited. So if I'm not constraining too much, I'm still in the microscopical regime. If I'm constraining a lot, I can maybe forget about these variations and I will just get a constant. Right? So it really depends on what feature you want to look on. how this potential is constructed, what is the Hamiltonian, etc., etc., I will show to you next week. There will be still some Fourier transforms again, just to show that it works, but there are not going to be some large summations with a lot of Fourier transforms and delta functions. Right? That's it for today. I will see you next week.
Thank you.
What did it teach?
We solved masses in a spring. That is dispersion relation, phonons, and
Okay. So he asked me to talk about the Ising model. What he basically saw in his course, statistical mechanics. So that's what I do today. My name is Lena. Is my handwriting small? Is it okay? You can see it? I see it here.
yeah.
Okay. And you can ask me about whatever you talk to me. Yeah, okay. Are there any technical questions? Or Stas talked about everything?
match to quiz. כאילו הזכיר את הבוחן, זה שום דבר.
Okay. It's more than. Okay, so this is the Hamiltonian. We saw that, right? Before? Okay, that's right. There are two terms. This one is the coupling between spins, and this one is the effect of magnetic field. I'll call it H. So I just want to remind what you see in the Ising model. There are two phases. So you have like spins, and you have the other phase where they all face the same direction, which is like the better, like by the energy, because you get like all these terms are like add up, okay? And you, okay, so this is the other phase or ferromagnetic. And you have another phase where the spins face like all directions. So this is a disordered phase or paramagnetic. Okay. So you have an order parameter m. I'll explain explain it all in details. Okay, I just want to remind the big picture, which is the average SI. And in this case, since they all face the same direction, and is not 0, and in this case, M is 0. Okay? איך מחליפים את המקום? I'll upload it sometime in this week. Okay. So basically what we want to do is to calculate the free energy and then find the minimum of it, and this will tell us like what happens in the system. Okay, but we can't do that because of the coupling between spins. So first we do a mean field approximation. We replace SI by M plus delta MI. So there is this average what is it? Magnetization. Okay. And each spin deviates from that by a little. Okay, by a small delta MI. Which is smaller than M. Okay, so we plug it into the Hamiltonian. Okay, first I just want to plug it into the SISJ. Okay. Yes. So now I just do the multiplication. Okay, so up to this point it is accurate, but the mean field approximation would be to neglect this term because we assume the delta m's are small. Okay, is it clear by now? Okay. Okay, so I plug it into the Hamiltonian, and it should be the mean field Hamiltonian. This one? So it's this. Sorry. Yeah. just open the parentheses here, and is it clear? This one? Okay, tell me if I'm going too slow. Okay, so now we would sum each term, but first I want to talk about this one, this term. Ij. So we just we can do it like sum over I and sum over j, and the half comes from the fact that these spins are replaceable, and then we can call it ji. Okay, so this is ji, and since all the spins are the same, so there is no meaning to the I, so we can just say and j. Okay. Okay, so now to this term. So again, we break it into sum. So this so this is just this is sum over I S I minus M. Okay. So this is M J N. Sum I S I minus M. Yeah. Yeah, okay. So I plug it back in H. Okay, so when you get and I'll put the full calculation down. Okay. So okay, so this is like the effective Hamiltonian, and you see that it's there is no interaction anymore, and we have this effective field, like instead of the field we had to begin with. Okay. Okay, so now we can like try to find the free energy and then find an equation for M. So since there is no interaction, you can just do factorization. Just do a single particle partition function. So it will be Si equals plus minus 1. So now we plug here plus minus 1. Okay. And so we have this term twice. So V minus beta J M. And here it will be 2 hyperbolic cosines. And of course, Z equals what Zi. Okay. So now we can talk about the free energy. The free energy is F equals U minus Ts. And basically, this formula explains the phase transitions that we're going to see when we change T. Because when T is small, then the only effect on the free energy would be the energy. So the system would tend to go to states that are like lowest energy. But when you increase T, then there is also the entropy, and the entropy wants states that have like the most number of possible states. Okay. Okay, so. Okay, so even from that, you can again see that this looks like energy. You have like 2 to the power of 2, and this looks like entropy multiplied by this beta. Okay.
We still need to know J, right? Because what we did, we just named Ji and Jij, named it J, like one J, but we don't really know how the system interacts. Like,
Yeah, okay, so I actually forgot to say that. Jij is like the most general, and you can put many kinds of Jij. It could be like 1 for the neighbors and 0 for the others, so it would make nearest neighbor models. It could depend on the distance between spins. But you can see from like what we do that the specific values of J is not doesn't affect like the general thing that happens. Okay. Okay. Okay, so now we need to find the minima of the free energy. So we will take like, the free energy per site, and we want the derivative to be 0. Okay. So now I'm just taking the derivative. This is just the derivative of the line. Okay, so we got this implicit equation for m, and now we have to work it out. Okay, so the easiest way to do that is just to put like the both sides of the equation on the x-axis. So you have m, which is just a straight line, and you have a hyperbolic tangent of something. So it could be either this way, so you have 3 intersection points, or you can have something that is like this, and then you have only this one. Okay, so the
Plotted it for h equals to 0. Right?
yeah, sorry, we do that for h equals to 0. Yeah, and then I'll explain what happens when it's not 0. Yeah, okay, so what the transition point between these two behaviors will be when the straight line is tangent to the hyperbolic tangent. Okay, so okay, so we find like the slope of the tangents. And this is just 1 at m equals 0, so this is beta j. And it has to match the slope of m, so it has to be 1. And then we get beta j, which is 1 over k v t j equals 1. So we're interested in the critical t. Sorry for the. Can you see? Okay. So we get Tc equals to j over kb. to understand like the two sides of the TC. So when T is smaller than TC, okay, let's start with the larger. Then the equation has only one solution, which has to be the minimum solution. So we have something like this. And for T smaller than TC, we have three solutions. One is 0 and 2 on these intersection points. Now which ones are the minima? So we would look at the solution at 0 and try to figure out if it's minimum or maxima. So we have this Fm, and if we and we actually also took the derivative of that. So now we take another derivative. I'll write it on this side. Okay. So at m equals to 0, then this is just j means beta j, and beta is smaller than 1, right? So this is smaller than 0, so this is maximum. So it will have maxima here, and the solutions say here. It look like that. So these are the two minimas. So what would M look like? So we can look at M as function of T. So at T larger than TC, it will be 0. Okay, and then at some point TC. This word would start to get a little broad until you start to get these two words, which are like they are identical. So the system would have to choose if it goes to this one or this one. So if it goes to this one, to the positive one, the magnetization would go like this. And if it chooses the other one, it will go like this. It has to choose at this point. Now, what happens when H is not 0? Then in this case, one of these words would be better, like energetically. So it would get a little deeper, and this one would get a little more shallow. Okay. Do you have any questions? so again, to connect to what I said earlier about the two phases, then of course this one is the ferromagnetic and this one is the paramagnetic. The ordered and
I don't see it in the math. Like,
what?
like why when TC is larger than T, you get no, like, we have a single minimum, but it is a minimum.
What?
When T is larger than TC, we get
Yes.
a lot. We still have a minimum.
Yes.
So just not a double minimum. So why
This
is
one.
it because it is like definitive, like it is zero by definition. This is the meter. The
Okay,
minimum?
this equation has like one immediate solution that is m equals 0. You can see it both like by just looking at the equation, both here.
Sure.
Okay.
But how does that relate to TC?
How does it relate to TC?
Yeah, it is not like clear in the math to me.
Okay, so this is for a specific temperature, which is like related to beta, right? Beta is DKB. So assuming a specific temperature, you have to see how many solutions this equation have. And the effect of beta would be on like the shape of the tangent hyperbolic. Okay. So when beta is small or large? Okay, when beta is small, it would be like in this shallow shape, and it would not intersect again this straight line. But when beta is higher, then you have like these intersection points. So you have 3 solutions to M. That makes sense.
Okay, I guess. I just don't get why the solution is n. Like this single solution is like the trivial n equals 0. That's what you're saying.
Yes.
Okay.
Okay. Okay. So the transition between this picture and this picture is like continuous. At the transition point, it starts to get a bit wider, and then these wells start to form, but they start from 0 and then get a little apart. Okay, so this is a second order phase transition. And in second order phase transitions, you have universality, which means that systems with different, that are very different, act very similarly near the transition point. Okay, and you see this similarity by looking at the critical exponents. So now we'll talk about them. Basically, you define reduced temperature, which is T minus Tc over Tc, and then there are many critical exponents, but we will talk about 2 of them. Beta is a critical exponent of the magnetic magnetization, like how the magnetization acts close to the transition, like in this area. And you have the susceptibility critical exponent. The susceptibility is the effect of the external field on the magnetization. Yeah. Okay. So we'll start with B, with a beta. We again look at this equation, and I think we assume again that H is 0. So next to the transition, M is small, so we can do like a Taylor extension. And then just order the equation. So now just how do you say liberated? Okay, we just like want to find M squared. So it would be okay. So now we have to write it in reduced temperature terms. So we just write beta J. This is J over KBT, which is DC over T. This is DC. And this is 1 over 1 plus T. Why is that? Okay, so from here, okay. This way it's clearer. And 1 minus beta J susceptibility. So the trick is just to take the derivative of this equation, okay? Like of both sides. So we have so you can just like להעביר אגפים, and then you get this is the susceptibility, and it could behave differently at the two sides of the transition. Basically, it looks like the susceptibility looks like this. This is let's see. So we have the transition point, and it diverges at the transition point. Okay, and it could diverge differently. So we start with T larger than TC. So this one is simple. When T is larger than TC, then M equals 0. So we can just plug it in and take H goes to 0. Get and then again, like here, we plug this the beta J for here. Okay, so you can call it, say, gamma plus. So gamma plus equals 1. Okay. And now I'll write this equation this or and did it. I can erase. So we have the second, like I don't know, like the cosinus hyperbolic. So we'll use like this identity. And then we can use just this equation for H equals 0. Okay, so we plug it into susceptibility. now we have this expression for m squared, so we put it into the denominator. Back into pi. And then have this beta 1 minus t. So we can simplify that. And 1 plus t. Can I erase that? Get with the top. So far without. The denominator again, and again we plug this in, and then Taylor, you can say what this becomes 1 minus 2t, and again, so this is small, so we get again, this goes like t to the power minus 1, so gamma minus is also 1. Okay. So we got that gamma plus minus is 1 and beta is half. And basically this result is accurate and only for dimensions that are larger than 4. The dimensions could go into the J, the coupling factor, and you will see that probably in next lecture why maybe. Why is it true? Yeah, so basically that's it. I finished early, but I just want to briefly say what we did, okay? So we talked about the Ising model. We saw how you do the mean field approximation to it, which is basically saying that that what happens to every specific spin doesn't matter, but like the collective behavior of all of them, or the maybe the average behavior. And after that, we got something that we could solve, and we found we used the free energy to find the basically the phase transition and the behavior next to it. Okay. I know it wasn't very clear, so if any of you want to talk to me anytime, you can do that, and I'll also upload notes to the Lambda, which I hopefully will be clearer. Have any questions?
Does critical exponents also appear like a theory which are not midfield? This is very typical to any midfield theory.
Yes. The critical exponents appear in any system that has, like in any second order phase transition, and we found them using the midfield approximation, but you can find them like not using it, maybe even numerically you can find them. And in other methods you can see that this is not true for any case. Like we got that it's true for Ising model in any case. It doesn't matter what interaction you have, for example, but this is not true. Okay? Like this is one of the limitations of the midfield approximation. Okay, thank you.
תודה רבה.
Change over 0.
הבנתי.
זה שווה 1 בסוף.
אתה בטח ראית? אוקיי, אז אני אסביר לך. גזרנו פעם אחת.